So we've rephrased linear approximation in terms of a differential, which emphasizes the change in a function caused by the change in its input, as opposed to just the raw input and output values. That might seem like just merely a curiosity. It might seem like most of the time you would be more concerned with input and output values, but there's actually one common situation where it's the changes in values that are actually the more important things. And that's when we're talking about error. So suppose we have a spherical cell under a microscope that we've measured to have a radius of 4 micrometers. But there's an error with any measurement, and so suppose this measurement has a possible error of plus or minus 0.01 micrometers. Let's calculate the volume of the cell, but let's also approximate the error in the value for the volume that we calculate. So this error in our measurement is sort of going to propagate forward through our calculation to produce an error in the value for volume that we ultimately calculate. And the thing to notice here is that since typically errors are relatively small compared to the size of the measurement that they are errors of, we can use differentials to approximate these errors because the changes are small. Remember, differentials are good approximations when the change from the base point is small. And compared to 4 micrometers, 0.01 micrometers is pretty small. So 4 micrometers, this is a radius, so let's call this r. And plus or minus 0.01 micrometers, this is sort of a small change in r. So we could call this delta r, or I'm going to call it dr. All right, we want to calculate the volume of a cell, so that would be v. And we want to approximate the error, so the error would be delta v, but we're going to approximate it using dv. So to calculate all of these things, we need to know the relationship between the radius and the volume of a cell, but it's a spherical cell. So for a sphere, volume it's a formula you can look up. The ancient Greeks figured it out. It's 4/3 pi r cubed. Turns out to be the right number. Well, we need to know, so we can use this formula to calculate our volume. So our volume is 4/3 pi, and then our radius is 4 micrometers. 4 cubed is 64, I think, times another 4, 256 maybe? I'd better double check. So 4 to the 3rd power, 64 times 4, 256. Okay, so 256 pi over 3. Just might as well get a decimal approximation for this. 268.08. And this is cubic micrometers. Micrometers? Micrometers? Not sure. Okay, so that's the volume of this cell that we calculated. But what about the error? So an error is a small change, so we need to find dv. And dv is, since v depends on r, dv is dv dr times dr. And dv dr we can calculate. That's just the normal derivative. So, right, 3 comes down, cancel that third, the r cubed turns into r squared. So it's 4 pi r squared dr. All right. So our error is approximately dv, which is this. But notice that this expression, it depends not only on dr, but it actually depends on the value of the radius that we measured. So when we evaluate this, we need r and dr. So the r value for the radius we measured was 4 micrometers. And the error in this was plus or minus 0.01 micrometers. All right, now putting this all together, let's see, 16 times 0.01 is 0.16 times pi. Oh, I made a mistake. This should be squared, so this isn't right. So it should be 64, not 16. So, 0.64 times pi, and here we have micrometers squared, and then another one, so micrometers cubed altogether. So 0.64 times pi, that's 2.0106 cubic micrometers. All right, so our volume, the volume that we get for this cell is 268.08 plus or minus 2.0106 cubic micrometers. All right, so there are two important things to notice about this. First is that this same error in R would cause a larger error in the volume if the radius were larger. Right? dV depends not only on dr, but also on the value of r itself. So a given absolute size in error, a certain value for dr, could give you more error or less, depending on whether the radius that you measured was bigger or smaller. The second thing to notice is that you really do need this r here for the units even to make sense, because dV, it should be a volume, so it ought to be in cubic micrometers, but 2 factors of micrometers comes from this radius, and the other factor of micrometers comes from this error. So we really do need both pieces here. So both pieces have to be here for this to make any sense at all as far as the units are concerned. There's another variation on error, and that is, sometimes it makes more sense to measure error compared to the size of a thing, and that's called relative change or relative error. So if we have some quantity f, the relative change in f is delta f over f, so the change in the thing divided by the thing itself. Of course, if we're talking about small changes, then we can approximate delta f with df, so df over f. So we can calculate relative changes by calculating a differential divided by the original thing. As an example, it turns out that the flux or the flow of blood through a blood vessel is proportional to the 4th power of the radius of the blood vessel, so like this. When I say proportional, what that really means is that it's a constant times. So the flux is a constant, which we don't know, but let's call it k, times the 4th power of the radius, like this. So let's find a relationship between the relative change in R and the relative change in the flux. So the relative change in R, that's going to be dr over r, and the relative change in flux, that's going to be df over f. All right, so how could we use this? A relative change it's like a percentage change. Right? It tells you how big the change is compared to the size of the original thing. So a relative change of 0.5 means that the change was half as big as the thing to begin with. So let's see if we can find a relationship between these two relative changes. Well, I guess we should start out by just calculating df, since we're going to need to know that. So df, well, df is, just by definition, it's df dr times dr. And we can calculate df dr. We can just calculate this derivative. So it's 4 times k times r cubed. So that's, right, this part right here is df dr. And now we need to multiply by dr. Okay. Now we want to find a relationship between the relative change in the flux and the relative change in R. So I guess we should take our expression for df and just divide it by f. So df over f is, well, df is 4kr cubed dr. And now we're dividing by f, and f is k times r to the 4th. Well, now we can start simplifying things. Oh, this is a 4th power, not a multiple of 4. There we go. Now we can start simplifying things. So first of all, these k's drop out. We have a factor of 4 out here. And then most of these r's drop out. There's one left, though. So 4 times dr over r. Okay. Well, so right here, this is the relative change in F, the flux. And what we got is 4 times, well, d over r, that's the relative change in r. So the relationship between these relative changes is that the relative change in the flux is 4 times the relative change in r. So what this is saying is, if you change if the radius of a blood vessel changes by 1%, say, the change in flux through that blood vessel will change by 4 times as much, so 4%. And that's true no matter what, because these are relative changes, that's true no matter what the starting value of the radius of the blood vessel is. A change in 1% in radius will always cause a change in 4% in flux, even if it started out big or small.